In this video, we will learn the definition of topology and we will also discuss some example. Topology can define in different ways. Here, we will define topology via open set. Okay. So, if you have a set X, then topology is just a collection of subset of the set X which satisfies some property. Okay, we can write the definition. So, let X be a non-empty set, be a non-empty set. Okay. Now a collection, we are defining that collection by tau. So topology first letter is tau, so this is Greek letter T, tau, of subsets of X, of the set X, is called a topology on X if it has the following properties. If it has the following properties. So it needs to satisfy some properties. So what is the first property? First property is the empty set and the whole set should be in tau. The collection of subset, in collection of subset, the empty set and the whole set should be in that. Now properties B is if A1, A2, AN are in tau, then their intersection would be also in tau. AI would be in tau. So if you have different subset, then the intersection would be also in that set, in that collection tau. And third property is if AI where I element of I, this is index set, and this I can be countable or uncountable index set. Okay, this can be countable or uncountable. If a element of tau, then their union would be also in tau. So for I element of I, AI would be also in tau. So three properties. First one is the empty set and the whole set would be in that collection tau. If there are finite number of subset, then the intersection would be also in tau. If there are finite or infinite number of subset, then their union would be also in tau, where I is countable or uncountable index set. Then the pair, so this tau is called topology, and the pair, the set X and tau is called a topological space, topological space. Okay. Now we can discuss some example. So our first example is examples. So X should be a non-empty set. So we can define let X is a set which has three elements 1, 2 and 3. Okay. Then number 1, if if we think the collection is empty set and x would be always in tau, okay, because empty set and x would be always in tau, and we take another element 2, then this is a topology. This is a topology on x. We can check. So first condition, empty set and x, it satisfies, and second condition is if there are finite number of sets, subsets, then their intersection would be in tau. So if we consider these two, so what is their intersection? For this intersection is empty set, so empty set is already in tau. If we consider these two, so what is their intersection? Their intersection is 2, because x is 1 2 3 and 1 2 3 and 2 is intersection is 2 and 2 is already in that collection. Now third property, their union would be also in tau. Now if we consider first two, then what is their union? Empty set and x, the union is x, right? So x is already in that collection. Now if we consider these two element, these two, then what is their union? Their union is x. This one and that one, their union is 1 2 3 and 1 2 3 is x, which is already in tau. If we consider this one and that one, their union is 2 is already in that collection. So this is a topology. If we consider this one, tau equals to empty set x, then element 2, then element 1 2, then subset 2 3. So this is also a topology on x. We can check the property again. So first property satisfies because empty set and x is already here. Now second property, if we consider these two subset, then their intersection should be in that collection. So what is the intersection of this one and that one? Their intersection is 2 and 2 is already here. If we consider this one and that one, what is their intersection? Intersection is 2 and 2 is already here. If we consider this one and that one, so what is their intersection? The intersection is 2 and 2 is already here, okay. If we consider any other set, union, if we consider union, what is the union of this one and that one? Union of this one and that one is 1 2 is already here. If we consider union of 2 3 and 2, their union is 2 3 and 2 3 is already here, okay. So you need to check for all elements, okay, for all of them. So this is topology. Now next example, so if we think tau equals to empty set x 1 2 and 2 3, is it a topology? The answer is no. Why? Because if you take union of this one and that one, the union is 1 2 3, that is already here. That's true. That means this one, that one satisfied. Sorry, this one and last one. But how about intersection? If you take intersection of this one and that one, their intersection is 2, but 2 is not in the collection. So this is not a topology. Is not a topology on x, because the intersection is not on the collection. Now fourth example is the tau is, if you consider the empty set and the whole set, this is also a topology. This is called trivial topology, okay. Is a topology. So this is called trivial, okay, trivial topology, trivial on x. only empty set and X. So it satisfies all of the properties. First property already satisfies. Second property, if you take the intersection is empty set, which is already here. If you take the union, that is X, that is also in here. So this is a topology. I would now fifth example, if you consider tau equals to the power set of X. What is the power set? That means collection of all subset. Power set means collection of all subset of X. So first consider empty set, then X, then 1, then 2, then 3, then 1 2, then 1 3, then 2 3. Okay, so how many we have? 1 2 3 4 5 6 7 8. So 8 elements, because we know we should have 2 to the power n subset. 2 to the power n subset, and here n is 3, 2 to the power 3 is 8. So we have 8 subset, and this is a power set of X, and this is a topology. Is a topology on X. This is also called power set. Okay, power set. Thanks for watching.